Well, thank you once again, Mr. President. I didn't expect to be back on the podium quite so soon. I'm in thinking about what to speak on today, because it could have been on glaciology, modern ice sheets and their links to sea level rise, but I'm delighted in the context of the President's very kind words that I chose to talk about the marine geophysical signature of past ice sheets, because he was kind enough to highlight the Atlas of Submarine Glacial Landforms, which was recently published as a memoir of the Society. So I'm going to draw on that work, and of course the work of a number of colleagues who've worked with me on this over the past decade or so. How is this?
Green one to go forward?
Yeah, it's not working. Oh, there we go. Okay, super, yes. So first of all, what is the glacier-influenced marine environment? We're talking about these yellow lines, which cover today the bottom 20 or so % of the global oceans. But under full glacial conditions, the last time 20,000 years ago, they actually, I don't think this pointer's working either.
It's the white one.
Yes, it doesn't seem to be working. But anyway, don't worry. That's okay. 25% of the world's ocean was covered under full glacial conditions. But what do we know and what don't we understand yet about the glacier-influenced marine depositional record? From the variety of submarine glacial landforms, of which I'll show you some examples in a moment, we can draw quite a lot out about past ice extent. We can draw various things out concerning aspects of the dynamics of ice flow, including streaming and flow switching of important ice streams. We know something about deglacial retreat style, and we even know something about the application of modern Quaternary analogues to ancient rocks, such as the late Ordovician of Northern Africa. But, and of course this is one of the things we all appreciate about science, there is much more that we need to know. Firstly, we don't know enough about processes of landform genesis, often because these processes are hidden under several kilometres of ice. We need to know more about the rates of landform development. This is a chronological problem in part. We want to know what the landform distribution means for past environmental conditions, because this helps us reconstruct paleo-environment and paleo-ice sheets. And also, as we increase the resolution through new geophysical techniques and the refinement of existing ones, we find increasing complexity in the system. So I want to talk a bit about these things now. Firstly, the variety of submarine glacial landforms. And here are just a few examples taken from the Atlas of submarine glacial landforms. Beneath ice sheets, we find characteristically that the sediments, often relatively soft and deformable with low shear strengths, the sediments which effectively piggyback and give ice its high velocity of kilometres and sometimes more than 10 kilometres per year, are streamlined. And when, as we see in each of these examples, the ice itself has retreated, we find that under several hundred metres of water, such sedimentary landforms are absolutely beautifully preserved. At the top left, we can see large-scale lineations, over 20 kilometres or so long, but just a few metres in height. Very delicate features preserved since ice retreat about 15 or 16,000 years ago. Below them, we can see mixed beds, where the bed transitions between a rock bed, which provides the upstream core of many of these streamlined sedimentary features, and the streamlined downstream tails of them. And then, to look at the bottom right, we also find that there is an imprint of the subglacial hydrological system at the base of ice sheets, which is also important, particularly where we have strong surface melting to provide that meltwater source. And then, as well as landforms produced beneath ice sheets, we have landforms produced at the ice margin. These are classically the moraine systems that we all heard about at school. Some of them enormous. On the top left, west of Norway, a moraine system several hundred metres high and 50 or 60 kilometres around. Much smaller, delicate systems on the top right and below, and again, an ice marginal feature. Very delicate ridges, just a few metres high and perhaps of lateral continuity of only a few tens of meters to a kilometre or so. And these little features are produced annually, and you can count these back almost year on year. What happens is, during the summer, icebergs are carved from tidewater floating margins of ice masses. During the winter, the sea ice cover reduces the amount of iceberg production, and the ice, even though it is in general retreat almost everywhere in the icy world today, advances by a few meters to a few tens of meters, pushes up a little ridge. So this is 3 steps back, half a winter step forward, and so on and so on and so on. And we can demonstrate where we have air photography in these areas too, that these ridges are often produced annually. So our ice marginal landforms vary from these tiny, delicate things to, at the bottom right here, the huge trough mouth fans, of which the Bear Island fan is one of the most largest examples in the icy world, which the Bear Island fan is, in terms of volume, the same size as the Mississippi fan, produced over almost the same period, but with a hugely different internal stratigraphy, because it is not made of sorted sediment, it is made 95% of diamictic sediments, which are actually the product of basal processes beneath the ice sheet. And we can actually look at all these different landforms and look at their scale by volume along the bottom and by time on the y-axis. And we find that some landforms are produced almost instantaneously. The little berms, or sometimes the quite big berms, produced as icebergs gouge through the seafloor, are formed almost instantly as the iceberg keel impinges on the seafloor. Whereas on the right, we have the huge trough mouth fans. You'll also notice in this diagram that the dotted lines are more frequent on the vertical than the horizontal axis. And that is a reference to what I said at the start, that we don't know enough about the chronology, the time period over which many of these landforms are actually produced. But when we bring them together, they produce very imposing suites of landforms. This is a small cross-shelf trough cut into the margin west of Norway that you can see there. And we find a trough mouth fan at the outer edge. We find the streamlined sediments produced at the base of a former fast-flowing ice stream draining the interior of the Scandinavian ice sheet. And then we find at the shear zone, 18 to 20,000 years ago, between the fast-flowing ice that cut the trough and the lateral margins, we find at that shear zone a lateral shear margin moraine, which marks the paleo position of the suture between fast and slow-flowing ice. And then, if we move to the shallow banks between the many cross-shelf troughs on, for example, the Norwegian margin, we find a completely different set of landforms. Whereas in the trough we have fast-flowing ice and streamlined landforms in the direction of past ice flow, on the shelf in between we find much smaller, often transverse to flow features, marking the slow retreat of probably a much less dynamic, and in some cases perhaps even frozen in part to the base of the continental shelf, a much slower and less dynamic part of the ice sheet. And we can summarize this in 2 very simple block diagrams. Firstly, down here, ice stream glacial landform assemblages, which are dominated by the trough mouth fan at their margin and streamlined features in the direction of past ice flow. And on the left, we can see the transverse ridges that represent the slow retreat of ice often generated and produced through smaller drainage basins in inter-ice stream areas. And of course, we can use then this material in order to say several things, most simply, about ice extent and initiation. This is the traditional view of the Greenland ice sheet. At 18,000 years ago, the margin in northeast Greenland was always said from the Quaternary terrestrial record to be almost in the same position as under full glacial conditions. And the reason for that is simply because it was very cold in northeast Greenland under full glacial conditions. It's very cold today. Precipitation was probably very low under full glacial conditions. Where was the mass to drive the ice sheet out onto the continental shelf at full glacials if it was so dry there? We were lucky enough to be one of the first ships ever to be able to penetrate through the thick sea ice cover of northeast Greenland generated through the cold Greenland current. You can see the wiggly ship tracks as testament to that. And what we found in going across that continental shelf, almost for the first time with multi-beam echo sounders, is a series of these parallel to flow glacial lineations. It's very simple. If these are present, we know that ice was there, and we know that the ice was fast flowing. So simply by making the first observations here, we can show that the ice extent was probably at least 200 kilometres further than was thought. And that means we've got to look at the paleoclimatology of that part of Greenland in order to understand why the ice was able to advance in that sort of way. Very simple, but very important. Similarly, if we look back using 3D seismic data to paleo surfaces, and these are buried hundreds of meters below the present area of the Norwegian shelf, and we can see a series of iceberg plough marks. And these go right back through the stratigraphy of the Quaternary of the Norwegian margin. We can see some of the iceberg plough marks cut into the reflectors just here. And they show very directly that ice was present on the Norwegian margin to sea level and actually ploughed through these sediments right back to the beginning of the Quaternary. This is important because this is proximal to the source. What we've done in the past is we've looked at ODP records of iceberg rafted debris and the initiation of iceberg rafting in the far field. What was the provenance? We can sometimes work it out, sometimes we can't. But here we've got direct, rather than at a distance, evidence of the initiation of the growth of an ice sheet. Next, what about ice sheet flow dynamics? Here is a composite of several years of cruises to the Antarctic Peninsula margin with a number of colleagues from the British Antarctic Survey and ships of several nations. The scale is almost 200 kilometres from the bottom to the top. We can see a series of streamline features, and up towards the top, we can actually see grounding zones where the ice has stood still for a while during retreat. And we can infer from this the presence of a paleo ice stream filling this large 370-kilometre long and 100-kilometre wide trough. And we can map such features as cross-shelf troughs throughout the Arctic. We can map in red both the cross-shelf troughs and in that sort of browny colour. We can map the depot centres that are produced at their margins, the big trough mouth fans that are so characteristic of these things. And we can then utilise that information, and here is an example from almost 2,000 kilometres of the margin of Norway, from the Skagerrak and the North Sea in the south, right up to the north of Svalbard in the north. And we can utilise these subglacial landforms, the streamlining and the presence of former ice streams, to map those ice streams right the way through that margin. And this, in turn, provides a considerable but simple challenge to numerical modelling of past ice sheets. We can see here's a numerical model from a few years ago, and that model can produce the gross shape of the ice sheet. It can actually reproduce, by and large, the position of the margin of the ice sheet, but there is very little segmentation of flow in that. And this is one of the new challenges for ice sheet numerical modelling. Can the models of the last full glacial and deglaciation actually match the positions of fast and slow flowing ice? This is crucial. These are modern maps of the Antarctic and Greenland at the same scale. And we can see the white, the purples and the blues snaking back hundreds of kilometres into the ice sheet. Those fast flowing ice streams drain the vast bulk, up to about 80% of the mass, from the Antarctic ice sheet. If we want to understand the way paleo ice sheets behave, we have to know where these are, and we have to be able to model them numerically. And this is what our submarine land system models actually enable us to do. And we need now to refine the boundary conditions in ice sheet numerical models to do that. And we can go further back. This is very nice work. You can't quite see it. It's chopped off, but I'll say it anyway. It's work by John Craig and Dan Laheron. John, I think, was here this morning. And this is actually taking notions of ice streams and landforms and sedimentology to do with the presence of former ice streams to the North African margin from 440 million years ago. And we can see 1, 2, 3, 4, 5, 6 big ice streams draining the Pan-African ice sheet, or at least a part of the northern part of that ice sheet, through its northern margin to the sea. And we can use the landforms in order to try to do that in the paleo record. Indeed, Dan and I have done some glaciological calculations of the amount of ice flux through these, and it fits really nicely with the likely paleo velocities of these things. What about the style of ice sheet deglaciation? and retreat. Again, simple observations. The observation here is of well-preserved, streamlined bed forms. The interpretation, because they're so well-preserved and there is nothing superimposed upon them since their deposition, we interpret rapid liftoff through thinning and warming of the ice surface and rapid ice retreat, therefore. Where we find these features have superimposed upon them big transverse to flow grounding zone wedges formed at still stands during ice sheet retreat, perhaps of decades and maybe even of centuries. The depot centres have considerable volumes of tens of cubic kilometres of material. There, in that case, where we see them superimposed on the fast-flowing indicators, the megascale glacial lineations, we can infer episodic retreat between grounding zones. And finally, where we find suites, which can be tens or hundreds of the very delicate, small transverse to flow moraines, we infer the slow retreat of a grounded ice margin. Now, we can look, and indeed we and our colleagues have looked at many troughs around Greenland, around the Norwegian margin, and around Antarctica. And we can probably, for 2/3 of the troughs in both those areas, now say which of those three styles of retreat has taken place in those areas. And the challenge again for numerical models is, can they do the same? And the answer at the moment is no. And we, of course, and a number of labs around the world are trying to find the answer to why. And that is to understand better the basal boundary condition and the paleohydrology of ice sheets. And so we can use a model such as this, a simple block diagram, streamlined features, rapid retreat, episodic retreat where we have the very large grounding zones, and slow retreat indicated by superimposed retreat moraines. And what about reconstructing past environmental conditions? We know that there is a continuum of environments in which ice reaches the sea, from at the warmest, places like southeast Alaska and Chile, where even rain has some influence on the basal hydrology of the glaciers that sit there, to the very coldest environments of East Antarctica, where the water temperatures in those kind of places are -1, -1.5. And even if icebergs are carved, and we see many icebergs being carved from East Antarctica in that image on the bottom right, where those icebergs are carved, they actually melt very little during their traverse of the inner continental shelf, and very little iceberg rafted debris is deposited on those kind of settings. Whereas, if we go to southeast Alaska or even Svalbard, there is a large amount of surface melting each year. There's almost none in most of Antarctica. That surface meltwater descends to the bed and provides an important mechanism for lubricating the bed and leading to past ice flow. So, whenever we read about glacial marine sediments and sedimentation, the question is always where on this continuum from warmest to coldest glacier-influenced marine environment the particular example sits. This is one from Svalbard, which is meltwater dominated. If you don't have surface meltwater at the base of an ice sheet, you instantly cut by about 3 orders of magnitude the amount of water that is available for basal lubrication, because basal melting alone will generate rather little meltwater at the bed. And here we see various forms of grounding zone fan formed at points where subglacial meltwater streams actually emerge from the subglacial plumbing system to the margin, building fans as they go. Then, if we go to a much colder environment, such as northeast or northwest Greenland, we find very little sorted sediment, mostly diamictic material derived from deforming glacier beds. And there, during ice retreat, we find these huge, sometimes buried in the stratigraphy from past glaciations, these huge grounding zone wedges, which mark still stands during paleo retreats throughout the Quaternary period. And we can put this together, and on the top left, we see a meltwater-dominated environment with lots of sorted material, eskers, fans, and so on. And if we come down to the bottom right, we see a very different environment dominated by diamictic material, grounding zone wedges produced during ice retreat, and submarine fans. And then, although this is more speculative, we would love to find some of this, and we've looked, and colleagues around the world have looked in the Antarctic. There is a lot of talk about the drainage of subglacial lakes. Where does that water go? Does it come to the margin? this is perhaps what catastrophic drainage of those lakes would look like in the sedimentary record. We have yet to find those, and that is a challenge for us. And then finally, what about the complexity of the system? As our tools increase in their resolution, and as we get more and more access to three-dimensional seismic data sets from industry, our world looks all the more complex. This is an old 2D reflection seismic line from the Norwegian margin back through the last 2.7 million years. And what we see here is that in some areas, the reflectors, which represent a paleo shelf and a paleo slope, buried deep beneath the present sea floor, in some places, those slopes are preserved. In other parts, the slopes have been eroded by subsequent ice sheet advances. So where those shelf slope systems, and in particular the shelves, are preserved, we can look right back through the Quaternary record, right back through over 20 glaciations, and see how the ice behaviour has changed through a full Quaternary ice age from 2.7 million years ago to today. And one of the things that we see is the intensification of glaciation during about the last 900,000 years, and the greater amount of ice yielding fast ice flow. So this is one way in which the latest technologies and our access to them have given us a completely new window through time on the behaviour of past ice sheets. And then at the other end of the spectrum, we can use ROVs and AUVs equipped with multi-beam echo sounding systems to look in very great detail at the processes and patterns that result going on at the margins of modern tidewater glaciers. And I think it's important to work this problem from both ends, to work it from the modern processes of sediment delivery and the formation of the landforms and the stratigraphy that we see in the record, and then to take that back both through the Quaternary and, if we can, beyond. And this is probably one of the best examples of a series of superimposed glacial landforms. We see, firstly, number one, old buried ridges from a previous surge or short-term advance of this particular 10-kilometre advanced glacier, which reached 100 years ago or so to the terminal moraine ridge in 3A. We see buried ridges, we see streamlined landforms from the latest advance superimposed on that. Then, when the ice reached its furthest point, the red ridge, there's the ridge itself and beautiful debris flows formed from the soft deforming sediments beyond. Then, as at the end of a surge, water, as we know from modern process investigations of surge-type glaciers, water is ejected from the base of the glacier, and water pressure in the underlying sediments decreases. The ice sits down and material is squeezed up into rhombohedral or boxwork-like basal crevasse-filled ridges. And then finally, as ice retreats, we see the spider-like annual retreat ridges. And this is the sort of complexity that we could see as we improve the resolution of, for example, the multi-beam echo sounder systems in the same way as we have access now to the 3D seismic data. So we know some things, we know some things quite well, but we are challenged, as always, by new evidence. And finally, how can we use this evidence from the subglacial submarine system, our window, our view from the sea? How can we use these data in order to test numerical models and past reconstructions of ice sheets? Thank you.
Over there.
I'm not sure this is working.
Okay, well, let's try and get the battery changed.
Yeah, wonderful material, Julie. With those longitudinal grooves that you can see where you've got fast evenness, what is it that's doing the grooving? Is it rock at the base of ice, or is it ice itself, which is sculpted?
This is a very good question. I'd actually preface that by saying, what is the evidence, rather than the simple observation that these are what we say they are. And the evidence on their formation actually comes in part from rather few but very detailed seismic investigations where seismic sections have been set up across, for example, the Rutherford ice stream in Antarctica. And there, through time, you can actually see these streamlines developing in what we know, because we've drilled into them, not me personally, but scientists have drilled into them, to be soft deforming sediments. So we know what their rheology is. So that's the preface, if you like. We do know that's what they are. And I think that's a really important starting point, that we want to pin everything with observations of formation and modern processes, and not just by some circular argument concerning various quaternary examples and the mere fact that they occur in cross-shelf troughs. There are some beautiful cross-sections that we and others have from, for example, the Marguerite Bay area of Antarctica, where we've got very high resolution sub-bottom profiles through those. And you can see quite clearly there that the material that is forming the megascale glacial lineations as they come out of the page towards you is part of that sedimentary upper 10 or 15 metres of deforming and deformable sediments. And therefore, they are part of that unit rather than having been eroded into it. So these are depositional landforms. I think it's very important that you look at, in detail, at the shape of them in order to establish that. So, sorry, that's quite a long answer to your question.
Question over here, Mike.
Oh, you've got a new one, good. Yeah, but that wasn't working.
Fascinating presentation, many thanks. In your last slide, you showed debris flows going off from the foot of the glacier, I suppose. Would they be diamictite as well? And if that is diamictite, can you distinguish it from the diamictite of an actual till beneath the, left behind, beneath the glacier?
Yeah, I think that's a very good question, of course. I mean, yes, they are by and large, they are almost always diamictic. Those are repeating features in almost, at the margins of almost every paleo-tidewater glacier that we see. We see the ridge itself, which is built up partly by glacial tectonic processes and partly by the delivery of subglacial deforming sediments to the ice margin, and then classically the failure on actually quite small slopes, just a couple of degrees, of those beautiful debris flows. And of course, we've sampled them on many occasions. And one of the big distinguishers between what we might call classical lodgement till that is formed beneath glaciers and is so well known as boulder clay in many parts of the UK, and this is, if you look at the shear strength is hugely different. The shear strength of these debris flows is very, very low. The shear strength of the lodgement till is much, much greater, considerably greater, because basically they are over-consolidated by the weight of the overlying ice. Now, the problem comes where you've got deforming sediments under high basal water pressure, so their shear strength is likely to be low, and where the ice retreats very quickly. So the sedimentary record, although subglacial, nonetheless is still very low in shear strength. And then it is very much more difficult to distinguish between the two. And indeed, because we're talking about some things that happened below ice on land, if we're talking boulder clays in Britain, and then we're talking about these things that are formed in the marine environment, a very careful look through them with a microscope can sometimes find micropel evidence of marine life in them too, which is of course an indicator that they are glacimarine rather than subglacial terrestrial. And the further back we go in time, like to the late Ordovician of Northern Africa, the more important these sort of things become. Now,
very good. I think I'm going to bring it to a close there in the interest of time. Julian, thank you very much again.